Dilations. So this is an important one. They're all important, but I think this is the one that changes translation, reflection, rotation. I mean, they're all different, but this one changes size. And so this one, I think, is slightly more important. You're jumping ahead. A dilation is a transformation in which the figure changes size, but still the same shape. Changes size. The pre-image and image are, did you say false? Is that what's supposed to look like? What do you think here? Pre-image and image of a dilation are blank. Similar. Not congruent. I put OST there because that is, I don't know, just something they want you to make sure to know. Dilating. This honestly goes back to Unit 4 when we did similarity. Scale factors coming back. Oh, well, here, I'm going to tell you right now. The scale factor, well, here, first of all, in Unit 4, it was like, here, to get from this triangle to this triangle, the scale factor might be like 3. Like you multiply by, or it might be 1/3 from that triangle to that one. It's what you multiply all the side lengths by. So let's say the scale factor of the dilation is the same as the scale factor between similar figures. Same idea. Because you're actually making a similar figure. So take 10 seconds. True or false? Don't say it. True or false? A dilation is a rigid motion. Circle one of those. True or false? False. See, Ava, this is what happens. Oh, that's what it's clear. Ava, it's clear. Oh, go ahead. False. Yeah, rigid motion means congruent shapes. It is not. This is the only one that changes. Sometimes they'll ask the question, and I will as well. Simply, you got to understand dilation is the only one that changes size. So I'll ask you some way, some form. List which ones of these transformations are congruent to the original. And every one would be, except if there's a dilation. Okay, now similar to rotations, we have to have a center that we dilate from, and by how much. So there was a center of rotation, there's a center of dilation. This section for now is just around the origin. Okay. But I could have a similar triangle like that. Now here's what happens. If I dilate around the origin, let's say by 2. All right, let's say I dilate by 2. It does two things. It gets twice as big, and it gets twice as far away from the point. Okay, but I could have dilated around a different point. Let's say it's this triangle. Let's dilate around this point by 2. Well, it's going to be twice as big, but it's going to be in this direction. So it's going to be more down here. All right, we'll get it more exactly. I'm just telling you the concept. It's going to get, it's by 2. It's twice as far in that direction, twice as far away, and twice as big. So the dilation was center C, so where we're for now to origin, and scale factor. So what are you dilating by? N. 2, 1/2. Here's how they write it. Now this is important. So it's going to be like, let's look below. XY arrow goes to 5x, 6y. And what it means is multiply the x coordinate. Just it's multiplication, scale factor. Multiply the x coordinate by the number. Multiply every y coordinate by the number. So it's actually a pretty simple one to apply. Just multiply. That's what I said here. Just multiply. Okay. Now here's a review from Unit 4. First of all, you cannot have a negative scale factor. Okay. It has to be positive. Second, if the scale factor is bigger than 1, it's getting larger. It's a stretch, an enlargement. If it is between 0 and 1, so 1/2, 0.4, 1/3, 1/5, 2/3, it's getting smaller. It's a reduction. Remember, well, between similar figures, you could always go both directions. For this one, you're always going to start with the pre-image, go to the image. So there will only be one direction to go. This is interesting. I don't often ask this, but sometimes. If the scale factor is 1, nothing changes. It's actually a congruent shape. Okay. I say here, sometimes they ask, what is the scale factor? For example, this one. So if they said, what is the scale factor? Notice that this was the original and this is the prime one. So they said, what was the scale factor? We're dilating around the origin. What's the scale factor? You count one of the sides, or you count slope. I say that here. Count the lengths or count the slope between the figures. So 1, 2, 4, and 2. So I would say that the scale factor is a half, not 2. That's because I was going from this one to that one. So half is far away, half is big. You also could have counted slope, like down 4, right 4, down 2, right 2. And you can see it's half. It's big. Okay, any thoughts before we try a few? Let's try number 1. List the coordinates. Just list. Do not graph. Or you can graph if you want. List the coordinates of the image under the transformation xy goes to 5x, 6y. Let me tell you, most of the time it's 5x, 5y. It's like the same number. But I threw this one in here like this, because I have seen it before with sometimes different numbers. So we're going to do that for this, for these points, quadrilateral. It's pretty simple. A prime, I'm just multiplying the x's by 5, so negative 15, and the y's by 6. So 4 times 6, 24. And that's it. So b, negative 2 times 5 is negative 10. 0 times 6 is 0. For C prime, 1 times 5 is 5, 0 times 6 is 0. For D prime, 2 times 5 is 10, 6 times 3 is 18. Okay, I'm going to move on quickly from that one. And then on 2, let's graph. So instead of listing the coordinates, we'll graph. Get a triangle at the right. And 1.5 xy goes to 1.5x, 1.5y. So you're just going to find the vertices of the triangle. That's a little tough to say. That's going through 3. I think it came out on mine at least. It did. So let me list them here. We got 0, 3, 2, negative 3. And this one down here, negative 2, negative 3. Okay, we're dilating by 1.5, x and y. It's getting 1.5 times bigger. So it's growing, greater than 1. And I just multiply each of these by 1.5. So let me write in blue here the transformed triangle coordinates. 0 times 1.5 is 0. 3 times 1.5 is 4.5. Hey, also, just like any of the other transformations, you can really take your original point, like 0, 3, and put it into the formula. Like that's what these really are, like translation, x plus 3, y minus 2, you just can put a coordinate in. Same with reflection and rotation, so we can actually plug those in if you want like that. The next one, 2 times 1.5 is 3. Negative 3 times 1.5 is negative 4.5. So that's 3, negative 4.5. And the last one should be the same, but negative 3. The only thing that changed was the negative 2. So negative 3, negative 4.5. So each vertex got 1.5 times further away from the origin. And the triangle overall is 1.5 times bigger. Let's answer one more question about this, because sometimes this is an important concept. Do the slopes of the preimage and image lines change? That slope, these two, do the slopes change? No. So now that's something you might say, well, on this one it didn't change, but another one it might. Actually, not true. For the slopes, when you dilate it, they're always the same. When you change, it's getting further away from something, but it's not changing the actual slope of whatever line you have. Not going to change. But 1 and 2, list and graph. Any questions on those two? Okay. Let's move on to something. It's still dilating, but just a little different. We're going to dilate a line. So I'm going to do it. I got 3A and 3B. Actually, this is it. I'm doing this, dilating a line, and then we're just going to make some true false at the bottom. All right, so dilate a line. Y equals 2x minus 3 by a factor of 3 around the origin. So what I want to do first is let's graph 2x minus 3. Remember, that's just the y-intercept is -3. Slope of 2. That's up 2, right 1. Up 2, right 1. And I can do more if I want there. All right, so that's the original. I'm going to dilate by a factor of 3 around the origin. So around the origin right here. I just said a minute ago, here's a line. If I dilate a line, the slopes are still the same. So my dilated line, let me just put, well, the same slope. It'll still have a slope of 2. The y-intercept will change though. I can really just, it's a dilation around the origin. It's a point. So I go to my y-intercept, which is 0, -3. And I'm just doing a normal dilating a point. Just multiply by 3. So if I multiply by 3, I would get 0, -9. So let me put in green down here. This is my y-intercept from my line. By the way, you also could have just done this. You could say, here, this is 3 lengths away from the origin, times 3. It needs to be 9 units away. That would be there. Okay, so the y-intercept is -9, and I do a slope, same slope, slope of 2. And so there's my line. Up 2, right 1. So I just wanted us to make some conclusions here then. When dilating a line around a point that's not on the line, so dilating on a line is slightly different, but when dilating a line around a point that's not on the line, we dilate around the origin, the slope is the same, but it's unchanged. The y-intercept is multiplied by the scale factor. And I put, therefore, here's our conclusion, therefore a blank line is formed. Any thoughts? That line to this line? Type of line? A parallel line is formed. All right, so I want us to build to that. Here's a line. You dilate around a point not on the line, like the origin, you get a parallel line. We could have actually made this, it's just slightly different when they give you the equation of line. Up here, we kind of knew that. Like this one here, these two lines are parallel. All of them were parallel. Same slope. Okay. Well, anything I can answer on that one, part A? Let's dilate the same line. It's still graphed up there, the black line, by a factor of 3, same factor, around 0, -3. So this time, I'm dilating around a point on the line. I'm dilating around a point on the line. We know the slope is the same. It's still 2. I'm dilating by 3, but it's around a point on the line. So I'm right here. I'm not dilating around 0. This point, if I dilate by 3, it's still going to be at the same center, right, the same spot. And that's the y-intercept. So I'll put y-intercept the same. So we don't have to graph. When dilating a line around a point on the line is unchanged. It's the same line. Okay. Well, let's try these at the bottom. Important facts about a dilated image. Some of these we kind of covered above, some of them might be slightly different. You're going to circle true or false, and this could be for any dilation. So you could have, like, if you want to think of, you're starting with a triangle maybe. You know, you dilate bigger or smaller, or it could be around a different point. Let's do it together. Corresponding angles are always congruent. So corresponding in this sense means matching. The one, so like this one and this one, or these two up here. What do you think? Are they going to be congruent? Yes. By the way, if you have a line, just like up here, you won't have corresponding angles. But if you have a figure, and there are corresponding matching, yeah, they will be congruent. Corresponding side lengths. That length and that length? False. They will not be. The only time is if the dilation is a scale factor of 1. They'll be congruent. Corresponding side lengths are always parallel. Yeah, that's what we just spent the last example on. Corresponding side lengths will be parallel. Oh, I say here, just a single dilation. So now if you involve a rotation, yeah, or a reflection, it might be, the final result might not be parallel. A single dilation will be. The triangles are congruent. No, they change size. False, they're similar. They're similar. What's the last one here? The new figure. So I have this pre-image. The new one, point, segment, triangle, whatever it is, will be a scale factor times as big or small, and a scale factor times as far away or close. True. Now the wording is that's a lot to take in there. It's kind of the wording I was saying though. That is twice as far away, or 3 times as far away, and 3 times as big. Scale factor times as big. All right. Well, that's it for dilations. That's the last thing for this semester, I guess. Last new thing. It's sad, I know.